step outside tonight, if the sky's clear, and look toward the constellation Orion. Find the left shoulder of the Hunter, the star that burns with a deep, unmistakable amber red, the star that even casual observers can pick out without a telescope or a star chart. That star is Betelgeuse. It is a red supergiant, roughly 700 times the diameter of our Sun, so large that if you placed it at the centre of our solar system, its outer atmosphere would extend past the orbit of Jupiter. It is nearing the end of its life. It is a star in the process of dying, bloated and unstable, burning helium and heavier elements in its core, while its outer layers have expanded into a sphere of diffuse, nearly vacuum-like gas, 700 times wider than the star it once was. When it finally exhausts its nuclear fuel, in perhaps 100,000 years, perhaps in the next few thousand, nobody knows exactly, it will collapse and explode in a supernova visible in broad daylight from Earth. And in between those two moments, in the phase it is in right now, the red giant phase, it is doing something to its surrounding space that would, if Earth were orbiting it, make the question of whether any of us are here at all a question with a very specific and very uncomfortable answer. If you enjoy videos that take the most extreme what-if scenarios in astrophysics and work through them with genuine scientific rigour, that don't just gesture at the strangeness, but actually follow the physics wherever it leads, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about this question is that it is a simple matter of temperature. People hear red giant and assume the scenario is straightforward. The star gets bigger and hotter, Earth gets hotter, the oceans boil, life ends. A kind of scaled-up version of running too close to a campfire. This framing is wrong in almost every respect. Red giant stars are not hotter than the Sun. They are actually cooler at their surface, which is precisely why they appear red rather than yellow-white. The crisis they create for surrounding planets is not primarily a crisis of too much heat in the ordinary sense, though heat is certainly part of it. The crisis is something far more profound, far more structure, and far more interesting than a simple roasting. It is a crisis of physics operating at multiple scales simultaneously, of orbital mechanics and stellar winds and atmospheric chemistry and tidal forces and radiation environment and geological transformation, all operating at once, reshaping a world in ways that require understanding each mechanism separately before you can appreciate how terrible they are in combination. The scenario we are about to explore is not Earth gets hot. It is Earth is subjected to a complete restructuring of every environmental parameter simultaneously, driven by a star that is itself in the middle of the most dramatic transformation in stellar physics. The difference matters. The details are what make this extraordinary. To understand what happens to Earth orbiting a red giant, you first need to understand what a red giant actually is. Not the simplified version, but the full physical picture of what is happening inside a star as it enters this phase. And to understand that, you need to start from the beginning of a star's life. The Sun has been burning for approximately 4.6 billion years. In its core, hydrogen nuclei, protons, are being fused into helium nuclei, releasing energy in the process by converting a tiny fraction of the fuse mass directly into energy via Einstein's E=mc². This process has been going on since before the Earth existed, and it has been remarkably stable, The Sun's luminosity today is roughly 30% higher than it was when the solar system formed 4.6 billion years ago. But this increase has been gradual and slow, spread over geological time. The Sun is currently in what astronomers call the main sequence, the long, stable middle period of a star's life, during which hydrogen fusion in the core provides the energy that supports the star against gravitational collapse. The Sun will remain on the main sequence for another approximately 5 billion years. After that, something fundamental changes. That something fundamental was one of the great theoretical achievements of 20th century astrophysics, worked out in detail by figures including Subrahmanyan Chandrasekhar, Hans Bethe, Fred Hoyle, and a generation of nuclear physicists and computational astrophysicists who built the mathematical framework of stellar evolution. Before their work, the life cycle of stars was not understood. Stars were observed to have different colours and temperatures: hot blue stars, yellow stars like the Sun, orange and red stars, but the physical sequence connecting these observations into a single coherent narrative was not established. The Hertzsprung-Russell diagram, independently constructed by Ejnar Hertzsprung in 1906 and Henry Norris Russell in 1910, plotted the luminosities of stars against their surface temperatures and revealed that most stars fall along a well-defined diagonal band, the main sequence, with a separate population of luminous, cool stars sitting above and to the right of this band. Those upper right stars were called giants, and later, for the most extreme cases, supergiants. Nobody in 1910 knew what they were. They knew only that they were different. The explanation came decades later, as the physics of nuclear reactions in stellar interiors was worked out. The giants and red giants are stars that have exhausted their core hydrogen and are running on the hydrogen-burning shell, the same physical mechanism we described above. This was confirmed not just theoretically but observationally, as increasingly precise measurements of stellar compositions and ages in star clusters revealed that stars in the same cluster, all formed at the same time from the same gas cloud, and therefore all the same age, evolve off the main sequence at different rates, depending on their mass. The most massive stars, which burn their fuel fastest, leave the main sequence first and become giants or supergiants. Less massive stars, like the Sun, spend longer on the main sequence before evolving. Stars less massive than the Sun, burning their fuel so frugally that their main sequence lifetimes exceed the current age of the universe, have not yet evolved off the main sequence at all. By observing clusters of different ages and seeing which stars have evolved into giants, astronomers confirmed the theoretical predictions with extraordinary precision. The red giant phase is not theoretical speculation. It is observed directly in thousands of stars throughout the galaxy at every stage of their evolution. We know what red giants look like. We know their temperatures, their luminosities, their sizes, their masses, their compositions. We can place them on the HR diagram and trace the paths of evolution with confidence. Red giants are as well observed and well understood as any class of object in astronomy. Among the most studied red giants is, of course, Betelgeuse, the star we opened with, hanging in Orion's shoulder, burning its characteristic amber red. But Betelgeuse is a red supergiant, not merely a red giant. The distinction matters. Red giants arise from stars of relatively modest mass, from roughly 0.5 to about 8 solar masses, and represent the expansion of such stars after main sequence hydrogen exhaustion. Red supergiants arise from much more massive stars, 10 to 40 solar masses, and are far larger, far more luminous, and far shorter lived. Betelgeuse, with a mass of roughly 10 to 20 solar masses, is a factory of nuclear reactions in a state of continual convective turmoil. Its outer layers, churning in enormous convective cells, each several hundred times larger than the Earth, that cause its surface to pulse and vary in brightness on timescales of months to years. The famous Great Dimming of Betelgeuse in late 2019, when it faded significantly in brightness and triggered widespread speculation about an imminent supernova, was subsequently understood to be caused by a massive surface mass ejection, a cloud of gas and dust expelled from the star's surface, partially obscuring it from our line of sight, followed by the cooling and darkening of a large region of the stellar surface in the aftermath of the ejection. It was a reminder that red supergiants are not peaceful objects. They are storms. The red giant that our solar system's sun will become is smaller than Betelgeuse, smaller by a factor of roughly 3 to 5 in radius, but the physics is the same in kind, if not in scale. Our Sun, classified as a G2V main sequence star, will follow the well-understood evolutionary track for a star of its mass, main sequence for approximately 10 billion years total. Then, a subgiant phase of a few 100 million years as the helium core grows in the hydrogen-burning shell intensifies. Then, the red giant branch as the outer layers expand. Then, the helium flash and the horizontal branch phase. Then, the asymptotic giant branch, and finally, the expulsion of the outer layers as a planetary nebula and the revelation of the white dwarf at the center. This entire post-main sequence evolution is well constrained by stellar models and confirmed by the observation of solar mass stars in clusters of known age. We know what the sun will become. We can calculate it. The uncertainty is not in the qualitative picture, but in the quantitative details. Exactly how large the sun will become at its maximum, whether it will physically engulf Earth or merely broil it while stopping just short of ingestion. The question of whether the sun will physically engulf Earth is actually somewhat uncertain, and it is worth spending a moment on it because the uncertainty reveals important physics. As the sun loses mass through its intensifying stellar wind during the red giant phase, the gravitational attraction of the sun on Earth decreases. A reduced gravitational pull means that Earth's orbital energy is slightly greater relative to the reduced mass of the star, which causes Earth's orbit to expand, to drift outward. This outward migration of Earth's orbit may be sufficient to keep Earth just outside the sun's expanding surface at maximum red giant radius, or it may not. The answer depends on the exact rate of mass loss and the exact maximum radius, both of which involve uncertainties in the physics of stellar winds and stellar structure. Some calculations suggest Earth will be engulfed, dragged into the expanding stellar envelope by tidal friction, spiraling inward as the stellar material engulfs and decelerates it, ultimately consumed by the outer layers of the star. Other calculations suggest Earth will survive just outside the maximum radius, emerging from the red giant phase as a scorched, airless rock orbiting the newly formed white dwarf. Either way, engulfed or merely scorched, the result is the same. No oceans, no atmosphere, no life, no recognizable connection to the world we currently inhabit. The stellar wind deserves much deeper treatment than we have yet given it, because it is one of the most consequential aspects of the red giant environment, and one that is less intuitively obvious than the luminosity increase. The current solar wind is a constant low-density outflow of charged particles, primarily protons and electrons, with a smaller fraction of helium nuclei and trace amounts of heavier elements streaming outward from the Sun's corona at velocities of 300 to 800 kilometers per second. The corona, the Sun's outer atmosphere, visible as the pearly white halo during a solar eclipse, reaches temperatures of 1 to 3 million Kelvin, far hotter than the photosphere below it, for reasons that are still not fully understood. This high coronal temperature drives the expansion of the solar wind. The thermal pressure is sufficient to accelerate the coronal plasma to supersonic velocities, and it streams outward continuously, filling the entire heliosphere, the bubble of solar influence that extends roughly 100 astronomical units in all directions before the solar wind runs into the interstellar medium and decelerates abruptly at the heliopause. The mass loss rate of the current solar wind is approximately 2 times 10⁻⁴ solar masses per year. At this rate, the Sun has lost a negligible fraction of its total mass over its lifetime, less than 0.1%. But when the Sun becomes a red giant, this changes dramatically. The mechanism of mass loss in red giants is related to the enormous size of the stellar envelope and the radiation pressure, the physical pressure exerted by light itself on the stellar material. When the stellar luminosity is high enough, the radiation pressure on dust grains and molecules in the outer stellar atmosphere is sufficient to accelerate them outward, driving a wind that carries with it a large fraction of the star's total mass. The mass loss rate in the red giant phase is estimated at 10⁻⁸ to 10⁻⁷ solar masses per year for a solar mass star, roughly 1,000,000 times the current solar wind rate. At the higher end, the Sun will lose several tenths of a solar mass during the red giant phase, a significant fraction of its total current mass of 2 by 10,300 kilograms. This mass loss carries enormous consequences. The first is orbital dynamics. As we discussed, the decreasing stellar mass causes Earth's orbit to expand. The second is the physical environment. The red giant stellar wind fills the inner solar system with a much higher density of particles than the current solar wind. At Earth's orbital distance from a red giant, the density of the stellar wind is perhaps 1,000,000 times higher than the current solar wind density at Earth. The impact on any planetary magnetosphere is severe. Let us trace this impact in detail. Earth's magnetosphere is generated by the geodynamo, the convective circulation of liquid iron in the outer core, driven by the slow crystallization of the inner core and the resulting release of latent heat and compositional buoyancy. This circulation of electrically conducting fluid in the presence of rotation generates a magnetic field through the same dyno mechanism that operates industrial generators. But on a planetary scale, and powered by geological heat rather than mechanical rotation. The magnetic field extends outward from Earth in a dipole configuration, roughly like the field of a bar magnet, but shaped and distorted by the solar wind into the characteristic teardrop shape of the magnetosphere, compressed on the sunward side by the wind's ram pressure, stretched into a long magnetotail on the downwind side. The magnetopass, the boundary where the solar wind's ram pressure equals the magnetotail, currently sits at roughly 10 Earth radii. Behind this boundary, the magnetosphere shields the inner environment from the solar wind particles. The solar wind does not reach Earth's surface directly. Most of it is deflected around the magnetopoles and flows around and past the Earth, confined to the magnetosheath between the bow shock and the magnetopoles. Only a small fraction of solar wind particles penetrate the magnetosphere, entering through the polar cusps, regions near the magnetic poles, where the field lines funnel down toward the atmosphere, and producing the auroral displays that occur when energetic particles rain down the field lines into the upper atmosphere and ionize the atmospheric gases. Under a red giant stellar wind, with a density and flux perhaps 1 million times higher than today, this balance is completely disrupted. The ram pressure of the stellar wind scales with the particle density. A millionfold increase in density produces a millionfold increase in ram pressure. The magnetic pressure of Earth's field, needed to balance this, is correspondingly greater, which would require either a magnetic field roughly 1,000 times stronger than Earth's current field, since magnetic pressure scales as field strength squared. A millionfold increase in required pressure needs a 1,000-fold increase in field strength, or a much closer magnetopause. Earth's field is unlikely to strengthen by such a factor. The geodynamo is constrained by the heat flow from the core and the composition of the core fluid. An extreme intensification is not expected. The more likely outcome is that the magnetopause is pushed in dramatically, from 10 Earth radii to perhaps 1 to 2 Earth radii, barely above the top of the atmosphere. At this distance, the magnetosphere provides little protection. The intense stellar wind particles penetrate into the upper atmosphere, driving spettering, the physical ejection of atmospheric atoms by particle bombardment, at rates far exceeding anything in the current solar system. Even with the magnetosphere present, the atmospheric erosion by sputtering under red giant wind conditions would be catastrophic on geological timescales, measured in millions of years rather than billions. The nitrogen and oxygen molecules of the upper atmosphere are dissociated and ionized by the particle flux, the ions then being swept away by the magnetic field of the stellar wind. The neutral atoms, unaccelerated by the field, are eroded by direct particle bombardment. Over millions of years, the atmosphere thins from the top down, losing mass to space at rates far exceeding the geological and outgassing processes that replenish it. This atmospheric erosion operates in parallel with, and in addition to, the thermal escape driven by the intense radiation. In the current solar system, Mars demonstrates what happens to an atmosphere when the planetary magnetic field weakens. Mars lost its global dynamo approximately 4 billion years ago, and without the magnetic protection, the solar wind has since eroded its atmosphere to roughly 1% of Earth's surface pressure. The red giant stellar wind is vastly more powerful than the current solar wind. And even a planet with an active magnetic field like Earth would face atmospheric erosion rates orders of magnitude beyond what Mars experienced. The atmosphere, in other words, is being attacked simultaneously from above by the intense radiation driving thermal escape and photochemical dissociation, and from the side by the stellar wind driving sputtering and ion pickup. The combination is devastating. On timescales of millions of years, significant fractions of Earth's atmosphere would be stripped to space, even while the surface temperatures are climbing and the oceans are boiling, and the geological record of the planet's history is being erased layer by layer by the advancing tide of heat. As the hydrogen in the core is consumed, what is left is helium, the ash of hydrogen fusion. Helium, unlike hydrogen, cannot be fused at the temperatures prevailing in the sun's core, so it does not generate energy. The core becomes inert, a ball of helium that generates no heat, provides no outward pressure, and sits passively as more helium ash continues to accumulate on top of it, from the shell of hydrogen burning that continues just outside the core. The core, without a heat source, begins to contract under its own gravity. The contraction releases gravitational potential energy as heat, the same mechanism that powered the sun before nuclear fusion began, in its protostellar phase. This heat flows outward through the star, and something remarkable happens. The layers immediately outside the shrinking helium core, finding themselves compressed and heated by the contracting core below, begin to burn hydrogen more vigorously than before. The hydrogen-burning shell becomes more powerful, not less, even though the core has effectively gone out. The increased energy from this shell drives an expansion of the star's outer layers. The outer envelope of the star, responding to the increased outward energy flux from below, inflates. It inflates dramatically. The Sun, which currently has a radius of 696,000 kilometers, will expand over the course of several billion years into a structure with a radius of roughly 200 times its current value, approximately 140 million kilometers, at its maximum red giant extent. That maximum radius is roughly equal to the current Earth-Sun distance. The Sun, at its largest, will extend out to approximately where Earth currently orbits. The radius alone does not tell the full story, because as the outer layers of the star expand, they cool. The surface of the Sun today, at 5,778 Kelvin, is hot enough to appear yellow-white and to emit light across the visible spectrum, peaking in the green-yellow range. As the Sun expands into a red giant, its surface temperature drops to around 3,000 to 4,000 Kelvin, cool enough that the peak of its emission shifts into the red and near-infrared, giving it the ruddy appearance that characterizes all red giant stars. Hence the name. Not red because it is hot, red because it is cool. The paradox of the red giant is that the interior is becoming more energetic. The helium core is contracting, the hydrogen-burning shell is intensifying, while the surface is becoming less energetic for unit area. The total luminosity increases dramatically, because the surface area is vastly larger, even though the temperature is lower. The luminosity of the Sun at its maximum red giant phase is estimated at around 2,700 times its current value. Not 2.7 times, 2,700 times as much energy as it does today, and it will pour it out from a surface that extends to where Earth currently orbits. This is the star that our thought experiment places Earth around, not the Sun as it currently is, but a star of roughly solar mass in the red giant phase with a luminosity of 2,700 solar luminosities, a surface temperature of roughly 3,500 Kelvin, a radius extending to roughly the current Earth-Sun distance, and a set of other properties, a stellar wind, a radiation environment, a gravitational influence, that together define the conditions in the surrounding space. And now the question becomes, where would Earth need to be to survive this? And what would it look like if it did? And what would happen to it if it didn't? Let us begin with the question of where the habitable zone is, because this is the organizing concept for thinking about what any planetary surface conditions would be under a red giant sun. The habitable zone of a star is the range of orbital distances at which a planet with the right atmospheric conditions could maintain liquid water on its surface, the so-called Goldilocks zone, not too hot and not too cold. For the current Sun, this zone spans roughly from about 0.95 astronomical units to about 1.37 astronomical units, where 1 astronomical unit is the average Earth-Sun distance. Earth is comfortably inside this range, which is why liquid water can exist on its surface, and why its surface temperature averages around 15 degrees Celsius. The inner edge of the habitable zone is set by the runaway greenhouse effect. If a planet is too close to its star, the water vapor in its atmosphere absorbs enough infrared radiation to trap heat until the oceans evaporate, creating a feedback loop that drives the surface to extreme temperatures, what happened to Venus, probably, in its early history. The outer edge is set by the ability of atmospheric carbon dioxide to maintain sufficient greenhouse warming to keep the surface above freezing. For a red giant with 2,700 times the Sun's current luminosity, the habitable zone is dramatically farther out. The habitable zone distance scales as the square root of the luminosity, so a star 2,700 times more luminous has a habitable zone roughly the square root of 2,700, about 52,000 times farther out than for the current Sun. The inner edge of the habitable zone around a red giant of this luminosity sits at roughly 50 astronomical units. The outer edge is perhaps at 80 or 90 astronomical units. For comparison, 50 astronomical units is roughly the distance of Pluto from the Sun, the inner edge of the Kuiper belt. The habitable zone for a mature red giant is way out in what is currently the solar system's deep outer reaches, the realm of Kuiper belt objects, of dwarf planets, of comets. The place where Earth currently orbits is not merely outside the habitable zone of a red giant. It is scorched, airless bedrock baking in a radiation environment hundreds of times more intense than anything that currently exists on Earth's surface. So let us run 2 versions of this thought experiment, because they reveal different aspects of the physics. Or later, they're a real red space race. In the first version, the version that answers the question most literally, Earth is currently at its current orbital distance of 1 astronomical unit, orbiting a red giant star of solar mass. We want to know what happens to it. In the second version, the version that answers the question in the most scientifically interesting way, we ask whether there is any orbit around a red giant at which Earth-like conditions could persist, and what those conditions would look like. Both versions are worth exploring in full. Begin with version 1. Earth is at 1 astronomical unit. The star is a red giant, 2,700 times more luminous than the current Sun, with a surface extending almost to Earth's orbit. The first thing to understand is that the planet does not simply get hotter in a way analogous to turning up a heater. The change is qualitative, not just quantitative. The solar constant, the power per unit area delivered by sunlight at Earth's surface, is currently about 1,361 watts per square meter. At 2,700 times the current solar luminosity, and at the same orbital distance, the power delivered per unit area would be 2,700 times larger, approximately 3.7 million watts per square meter. For reference, the most powerful continuous output lasers in the world, built for industrial cutting and welding, typically operate at a few kilohertz per square meter of beam cross-section. The intensity of radiation at Earth's orbital distance from a red giant would be 3.7 million watts per square meter, roughly 1,000 times the power density of an industrial laser, delivered uniformly across the entire hemisphere of the planet facing the star, continuously, without pause. What does this mean for the surface? The answer requires understanding something called the Stefan-Boltzmann law, the relationship between the temperature of an object and the power it radiates. Any object at a temperature T radiates power proportional to T to the fourth power. Earth currently achieves a radiated balance. It absorbs solar radiation and radiates thermal infrared back to space at a rate that balances the incoming power, at a surface temperature of around 255 kHz in the global average. Greenhouse effect pushing the actual surface temperature to 288 degrees Kelvin. If the incoming radiation is suddenly 2,700 times more intense, the radiative balance temperature scales as the fourth root of 2,700, which is approximately 7.2. The equilibrium temperature at Earth's orbital distance around a red giant would be roughly 255 Kelvin times 7.2, or about 1,836 Kelvin, approximately 1,563 degrees Celsius. At this temperature, the surface rocks are not merely hot, they are molten. The melting point of basalt, the most common volcanic rock on Earth's surface, is around 1,000 to 1,200 degrees Celsius. Granite, the principal constituent of continental crust, melts at around 700 to 850 degrees Celsius. At an equilibrium temperature of 1,563 degrees Celsius, the entire surface of Earth, every continent, every ocean basin, every mountain range, is a sea of liquid rock. Not metaphorically, literally, the planet becomes a magma ocean. But this equilibrium is not reached instantaneously. It is reached over a time scale set by the heat capacity of the oceans and the surface rocks, and on the way to that equilibrium, a sequence of catastrophic events unfolds that changes the planet's character fundamentally, one after another, before the final molten state is reached. The first thing that happens, essentially immediately, on a geological timescale, is the destruction of the oceans. We think of the oceans as permanent features of Earth's landscape, as ancient and stable as anything on the planet. But they are, in thermodynamic terms, extraordinarily fragile. Their existence depends on a narrow range of surface temperatures between 0 and 100 degrees Celsius, and more specifically, on the balance between the solar radiation received and the rate at which the planet loses heat to space. When the incoming radiation increases by a factor of 2,700, The oceans do not gradually warm. They undergo runaway greenhouse effect of unimaginable ferocity. The runaway greenhouse effect works like this. As the oceans warm, they evaporate more quickly, adding water vapor to the atmosphere. Water vapor is a powerful greenhouse gas. It absorbs infrared radiation and traps heat, warming the atmosphere further, which causes more evaporation, which adds more water vapor, which traps more heat, in a self-amplifying feedback loop. On Earth today, this runaway greenhouse is prevented by the relatively weak solar constant. The incoming radiation is not sufficient to drive the oceans to full evaporation, and the feedback loop stabilizes at current conditions. But under a red giant sun, the incoming radiation is not just slightly too intense, it is 2,700 times too intense. The runaway greenhouse proceeds not gradually, but at catastrophic speed. To appreciate the speed and the mechanism, it helps to trace the sequence year by year. In the first year of the red giant's influence at Earth's orbital distance, the surface temperature begins to rise rapidly. The oceans, which currently cover about 71% of Earth's surface and act as an enormous heat reservoir, their heat capacity is about 1,000 times greater than the atmosphere above them, begin to absorb the dramatically increased radiation. The surface of the ocean warms. Evaporation rates, which currently average the creamy civilization processes, increases the base masses. Over decades to centuries, as the ocean surface temperatures rise from the current average of about 17 degrees Celsius toward 50, 70, 90 degrees, the evaporation rates escalate dramatically. The Clausius-Clapeyron equation, the thermodynamic relationship between temperature and the saturation vapor pressure of water, tells us that the maximum water vapor the atmosphere can hold increases roughly exponentially with temperature, approximately doubling for every 10 degrees Celsius rise in temperature. As the ocean surface temperature rises from 17 degrees to 100 degrees, the saturation vapor pressure increases by a factor of roughly 10 to 15. The atmosphere becomes thick with steam. The pressure at the surface increases as the mass of the atmospheric column grows. The boiling point of water rises with increased pressure. At double the current atmospheric pressure, water boils at about 120 degrees Celsius. At 10 times the current pressure, it boils at about 180 degrees. The rising pressure continually delays the final boiling of the ocean, while the temperature continues to climb. But this is a temporary reprieve. The heat input is relentless. Over centuries to millennia, the oceans continue to warm. The surface layer heats to temperatures well above the current boiling point, sustained as liquid only by the increasing atmospheric pressure of the growing steam layer above. Enormous convective cells develop in the ocean, vast, slow-turning columns of hot water rising from the depths, replacing cooler water at the surface that evaporates into the increasingly dense steam atmosphere. The deep ocean warms more slowly than the surface, but it warms. The thermocline, the zone of rapid temperature decrease between the warm surface layer and the cold deep ocean, shifts downward and eventually disappears as the deep ocean warms to temperatures that would have been considered extreme even in the deep, most volcanically active oceanic basins. Throughout this process, the photosynthetic organisms that currently form the foundation of the marine food web are dying. Phytoplankton, the microscopic plant-like organisms that perform roughly half of all photosynthesis on Earth, living in the surface layers of the ocean, have a thermal tolerance that extends to perhaps 40 to 45 degrees Celsius for the most heat-tolerant species. Above this, the proteins that catalyze photosynthesis, the enzyme complexes embedded in chloroplasts, denature, losing their three-dimensional structure and their function. As ocean surface temperatures climb above 50 degrees, the last phytoplankton die. The primary production of the ocean ceases. The food web built on those phytoplankton, from zooplankton to small fish to large fish to marine mammals, collapses, bottom to top, in the space of perhaps a few decades. The ocean becomes a warm, increasingly lifeless soup of dissolved organic matter from the death of the ecosystem, slowly heating toward the boiling point. On land, the picture is similarly catastrophic, but follows a different sequence. The forests and grasslands and agricultural ecosystems that cover the land surface are, in most cases, firmly limited at much lower temperatures than the ocean. Most land plants cease function above about 45 to 50 degrees Celsius. Their leaves, exposed directly to the intense red giant radiation, heat rapidly above these temperatures, even if the air temperature is somewhat lower. The characteristic response of a leaf to extreme heat, closing its stomata to prevent water loss, reducing photosynthesis, diverting resources to heat shock proteins, works for modest temperature increases, but is overwhelmed when the surface radiation intensity is 2,700 times normal. Plants die. Their roots no longer hold the soil. Erosion accelerates. The land surface, losing its vegetative cover, darkens or lightens, depending on whether the exposed soil is darker or lighter than the vegetation canopy, changing the surface albedo, the fraction of incoming radiation reflected back to space, and further modifying the climate in complex ways. The ice caps and glaciers melt early in this process. When the global mean temperature rises a few degrees, the polar ice becomes unstable, and the ice albedo feedback loop accelerates warming further. The removal of the ice removes a significant reflector. Ice has an albedo of roughly 0.8, reflecting 80% of incoming radiation, compared to ocean water's albedo of about 0.06. As the ice is replaced by open ocean, the surface absorbs far more radiation, amplifying the warming. This feedback, which is a significant concern even for modest climate change on Earth today, is completely irreversible in the red giant scenario. The polar ice melts once and never returns, and the amplification it provides helps push the ocean temperatures toward the runaway threshold. The loss of the oceans has cascading consequences across every Earth system. The oceans are not merely a reservoir of liquid water, they are a critical component of the carbon cycle, absorbing carbon dioxide from the atmosphere and depositing it in carbonate rocks on the seafloor through the process of carbonate weathering. They are a heat sink, distributing thermal energy around the planet and moderating temperature differences between poles and equator. They are the medium in which life evolved and within which a large fraction of all living organisms currently reside. They regulate the chemistry of the atmosphere through gas exchange at the surface, absorbing oxygen produced by photosynthesis, releasing carbon dioxide through respiration, exchanging sulfur compounds, nitrogen oxides in trace gases. The ocean is not one system among many. It is the central hub through which most of Earth's major biogeochemical cycles flow. When the oceans are gone, every one of these functions ceases simultaneously. The carbon cycle loses its primary carbon sink. Carbon dioxide, produced by the volcanic outgassing that continues throughout Earth's geological history, builds up in the atmosphere without the oceanic reservoir to absorb it. The carbonate rocks on the former seafloor, limestone, chalk, dolostone, become firmly unstable at rising temperatures, eventually decomposing through a process called thermal decarbonation, releasing their stored carbon dioxide back into the atmosphere. The carbonate rocks of Earth's ocean floors contain an enormous reservoir of carbon, roughly 60 times the carbon currently in the atmosphere. And as these rocks decompose at high temperatures, this carbon is returned to the atmosphere as carbon dioxide, compounding the greenhouse effect catastrophically. The resulting atmosphere is not Earth's atmosphere with the oceans removed. It is a completely different atmospheric system, a thick blanket of carbon dioxide, water vapor, the steam from the vaporized ocean, sulfur dioxide from increased volcanic activity, nitrogen, and eventually at high enough temperatures, silicate vapors from the heated rocks. The atmospheric pressure at the surface climbs, first from the addition of steam, then from the decomposition of carbonates, potentially reaching pressures many times Earth's current atmospheric pressure. The surface, under this thick, hot atmospheric blanket, cannot radiate heat to space efficiently because the thick atmosphere is opaque to the thermal infrared. The temperature climbs further. The rocks begin to melt. As the surface temperature rises through the range of hundreds of degrees, the atmospheric conditions become increasingly extreme. Above about 1,500 degrees Celsius, ordinary silicate minerals, the stuff of rocks, begin to melt and vaporize into the atmosphere. Silicon dioxide, magnesium oxide, iron oxides, the chemical components of rocks, have appreciable vapor pressures at these temperatures, and they begin to contribute to the atmosphere, creating what planetary scientists call a rock vapor atmosphere. The atmosphere of the baked molten Earth is no longer primarily nitrogen and oxygen. It is a mixture of steam, carbon dioxide, sulfur compounds, and rock vapor, silicate gas, metal vapors. A chemical mixture so exotic it has no parallel anywhere in the solar system today and requires specialized, high-temperature atmospheric chemistry to model. The planet has become not just inhospitable, it has become a fundamentally different kind of object, a magma world with a rock vapor atmosphere, intermediate between a rocky planet and a gas-draped hot rock, classified by some planetary scientists as a lava planet, in theoretical models of very hot close-in exoplanets. But there is another factor we have not yet discussed, one that changes the picture significantly even before the surface reaches lava temperatures. It is the stellar wind. The Sun currently emits a steady stream of charged particles, protons and electrons, called the solar wind, at a rate of approximately 10⁻114 solar masses per year. This sounds like a small number, and it is. Over the entire history of the Sun, it has lost less than 0.01% of its total mass to the solar wind. But the solar wind is not negligible in its effects on planetary atmospheres. Mars, which lacks a global magnetic field, has had its atmosphere gradually eroded by the solar wind over billions of years, losing most of its original thick atmosphere to space. Earth is protected by its magnetic field, the magnetosphere, generated by convection in the liquid iron outer core, which deflects the solar wind and prevents most of it from reaching the upper atmosphere. Without Earth's magnetic field, the solar wind would gradually strip away the atmosphere over millions to hundreds of millions of years. A red giant star does not have the solar wind of the current Sun. It has something dramatically more intense. As stars evolve off the main sequence and expand into red giants, their stellar winds intensify enormously. A typical red giant loses mass at a rate of 10 to 20 solar masses per year, between 6 orders of magnitude and 4 orders of magnitude more mass loss than the current solar wind. The solar wind from a red giant is not a gentle stream of charged particles. It is a hurricane of material, sweeping outward at hundreds of kilometers per second, carrying with it the substance of the star itself as the star's outer layers are gradually expelled into space. This stellar wind plays a crucial role in the red giant's evolution. It is the mechanism by which red giants eventually lose their outer envelopes and expose their hot, compact, helium-burning cores, leaving behind what becomes a planetary nebula and a white dwarf. The stellar wind is the star slowly blowing itself apart. At Earth's orbital distance from a red giant, the stellar wind, 1,000,000 to 100 million times more intense than the current solar wind, would encounter Earth's magnetosphere with ferocity that dwarfs anything in the current solar system. The magnetosphere would be compressed dramatically on the sunward side, its boundary pushed down from its current position at roughly 10 Earth radii to perhaps 1 to 2 Earth radii, barely above the atmospheric layer. The increased particle flux would penetrate much deeper into the atmosphere, driving intense auroral activity and chemistry changes in the upper atmosphere. Nitrogen and oxygen molecules would be dissociated and ionized. Complex atmospheric chemistry would produce new molecules. More importantly, the intense particle flux would drive atmospheric escape. Atoms in the upper atmosphere, given enough energy by the impacting particles, achieve escape velocity and leave the planet forever. The stellar wind of a red giant, at close range, would accelerate the erosion of any remaining atmosphere on a timescale of millions to tens of millions of years, fast by geological standards, slow compared to the thermal effects we discussed, but operating continuously and irreversibly. The combination of the runaway greenhouse effect, the vaporization of the surface, and the stellar wind erosion would strip Earth of its atmosphere entirely over time. What remains after this stripping? After the oceans have evaporated, the carbon dioxide has been blown away, the rock vapor has condensed back to rock as the planet cools after close encounters, is a bare, airless rock, its surface scoured clean, its seas of ancient lava resilicified into a smooth, featureless plain, its mountains erased by the thermal expansion and recooling of the rock, its history of continents and oceans and biology preserved only in the subsurface geology, inaccessible to observation, sealed under a new crust formed from the solidified magma ocean. This is the fate of Earth in version 1. Not a dramatic explosion, not a Hollywood disaster. A slow, inexorable transformation. First an ocean-boiling runaway greenhouse lasting thousands of years, then centuries of molten surface as a magma ocean, then the slow cooling as the stellar wind will bound back again, primer, time, alter, and calamity in the science. Then the long, dark quietness of a bare rock orbiting the cooling remnant of what was once its sun. It is, in a word, thorough. The geology tells you it happened. There is no survivor to tell you how. But let us now step back from this particular orbit and ask the more interesting question. Is there any orbit around the red giant star at which something like Earth's current conditions could persist? At which liquid water, stable temperatures, and breathable air are possible? At which life, as we understand it, could survive? The answer, surprisingly, is yes, in principle. And working out the conditions under which this is possible reveals some of the most extraordinary potential environments in stellar astrophysics. We established that the habitable zone of a solar mass red giant at its maximum expansion and luminosity is located between roughly 50 and 90 astronomical units from the star. This is the orbital distance range at which the incoming stellar radiation provides enough energy to maintain liquid water on a planet's surface, but not so much that the runaway greenhouse is triggered. At 50 to 90 astronomical units from the current Sun, there are no rocky planets. There are only icy bodies, Kuiper belt objects, trans-Neptunian dwarf planets, the occasional long-period comet. These objects are primarily water ice, carbon dioxide ice, methane ice, and silicate rock, frozen solid at temperatures of 30 to 50 Kelvin above absolute zero. They have been sitting at these distances for 4.6 billion years, frozen, inert, lifeless. But when a star becomes a red giant and its luminosity increases dramatically, these frozen outer bodies begin to warm. The ices that have been locked in place for billions of years start to sublime, to transition directly from solid to gas without passing through a liquid phase, as the temperature rises above the sublimation point of each ice. A large Kuiper belt object, something with the mass of Pluto or larger, perhaps several times larger, possessing a substantial inventory of water ice and carbon dioxide ice, would, under the heat of a red giant sun, undergo a transformation that in some respects resembles the transformation of a comet as it approaches the inner solar system, but on a planetary scale. As the red giant heats these outer bodies, their surface ices sublimate, releasing gases that form a temporary atmosphere. The question of whether this atmosphere persists, or whether it too is stripped away by the stellar wind and radiation, depends critically on the body's mass and gravity. But a small Kuiper belt object, a few tens of kilometers across, has essentially no gravity to speak of. Any atmosphere it acquires is immediately lost to space. But a large body, something like Pluto, or better, a super Pluto, several times Pluto's mass, or a rocky body comparable to Mars or Earth that happens to orbit at these distances, has sufficient gravity to hold on to a thick atmosphere as the ices sublime. Here is the scenario. Imagine a rocky planet with roughly Earth's mass, one Earth mass of silicate rock and iron, that happens to orbit at 50 to 70 astronomical units from a star that has recently become a red giant. In the star's main sequence phase, this planet was frozen, locked in perpetual winter at temperatures far below the freezing point of water, its surface covered in ice, its interior cold and geologically quiet. When the star becomes a red giant, the warming begins. Over thousands of years, the surface temperatures rise through the range of dry ice sublimation, 195 Kelvin, through the sublimation of water ice, 273 Kelvin, toward temperatures compatible with liquid water, 273 to 373 Kelvin, at the appropriate pressures. If the planet has enough water, and there is good reason to think that rocky planets in the outer solar system accumulate substantial ice mantles, the sublimation of that water ice into an atmosphere, combined with the sublimation of carbon dioxide to provide greenhouse warming, could in principle produce a transient habitable environment. Liquid water, moderate temperatures, a thick water vapor-rich atmosphere. This is sometimes called the transient habitability of former icy worlds, and it is one of the genuinely intriguing possibilities in the astrobiology of stellar evolution. Not permanent habitability, not permanent Earth-like conditions, but a window, perhaps lasting hundreds of millions of years, a period during which the red giant's luminosity is elevated enough to maintain these conditions at this distance, during which a formerly frozen world experiences its first and only era of warmth. If life can arise quickly, if the chemical processes that produce prebiotic chemistry and eventually simple living systems can proceed on timescales of tens to hundreds of millions of years, then the former icy worlds of a red giant system are candidate locations for the emergence of life. Not life that has been there since the beginning, life that is brand new, born in the warmth of a dying star, living out its entire evolutionary history in the brief geological moment of a red giant's fire before the star cools and the world freezes again. This possibility, the idea that red giant stars might trigger the emergence of life on previously frozen worlds just as they sterilized the formerly habitable inner planets, is one of the most profound implications of stellar evolution for astrobiology. It inverts the usual picture in which stars provide the energy for life during their long, stable main sequence phase. In the red giant scenario, the life-enabling warmth comes at the end of the star's main sequence life, not during it, and the planets that benefit are not the warm inner planets. They have already been destroyed. The beneficiaries are the cold outer worlds, the ones that have been waiting patiently in the dark for their moment of warmth. But there is a problem with this scenario that must be addressed carefully: the duration. A red giant sun maintains its elevated luminosity for roughly 1 billion years, first on the red giant branch, where the helium core is contracting and the hydrogen burning shell is intensifying, then through the helium flash and the subsequent horizontal branch phase, and then through the asymptotic giant branch, the second, even more luminous red giant phase that a solar mass star goes through before it finally expels its outer layers and becomes a planetary nebula. The total time during which the luminosity is substantially elevated is on the order of 1 to 2 billion years. This is actually a reasonably long time. The history of life on Earth shows that the transition from simple chemistry to the first living cells took perhaps 500 million years, and the subsequent evolution of single-celled life occupied the next 3 billion years. If life can arise in 500 million years, the red giant habitable phase is long enough to produce living cells on former icy worlds, though perhaps not long enough to produce multicellular organisms or anything approaching intelligence. The more fundamental problem is not duration but chemistry. The outer solar system is not chemically identical to the environment in which life arose on Earth. The composition of icy bodies in the outer solar system is known from spectroscopic observations, and in the case of comets and Pluto, from spacecraft visits. These bodies contain water ice, carbon dioxide, carbon monoxide, methane, nitrogen ice, ammonia, and complex organic molecules. The building blocks of prebiotic chemistry are present, but the exact mix differs from the primordial Earth's ocean chemistry in ways that might or might not be fatal for the emergence of life. The organic chemistry of the outer solar system is dominated by carbon, nitrogen, oxygen compounds that formed in the cold, low-density conditions of the outer nebula, and it is rich in some precursors to biological molecules, amino acids, nuclear bases, simple lipids, but poor in others. Whether this chemistry can produce life under the right temperature and pressure conditions is unknown. There is also the question of the rocky core beneath the ice. For a large icy body in the outer solar system to become habitable under red giant conditions, it needs not just liquid water, but a geological substrate that can provide the mineral surfaces, the hydrothermal chemistry, and the chemical gradients that many theories of life's origin require. If the body is predominantly ice with a small rocky core, the geochemistry may not be rich enough. If it has a substantial rocky mantle, if it is more like a water-covered rocky planet with a thick ice crust than like a primarily icy body, the geological foundation for life's chemistry is more promising. Now, let us consider what the experience of being on the surface of such a world, a formerly frozen rocky planet at 50 to 70 astronomical units, warmed by the swelling red giant, would actually be like. Not from the perspective of its hypothetical microbes, but from the perspective of a human observer who could somehow be placed there, looking up at the sky and out across the landscape. The star in the sky is nothing like the sun. The red giant, viewed from 60 astronomical units, subtends an angular diameter of about twice the Sun's current angular diameter from Earth, but is far larger in absolute size and far redder and far less bright per unit area of its disk. The sky is lit not by the brilliant blue-white glare of a hot star, but by a deep amber-red illumination, like perpetual sunset. The star hangs large in the sky, perhaps twice the apparent diameter of our Sun from Earth, but its light is warm, diffuse, and predominantly red. Photosynthesis, if it has evolved on this world, uses this light. The pigments optimized for red giant sunlight are different from chlorophyll. They absorb in the far red and near infrared rather than in the green absorbing spectral ranges that characterize Earth's photosynthetic organisms. The plants on such a world, if they exist, are dark, absorbing the available reddish light efficiently, reflecting very little of it, appearing almost black to an Earth-adapted human eye. The sky itself is not the deep blue of Earth. With a red star providing the illuminating radiation, and with an atmosphere whose composition differs from Earth's, the scattering of light in the atmosphere produces a sky that might range from orange-yellow during the day to deep red at the low illumination equivalent of dusk, with stars visible even during daylight, the stellar background unbleached by the blue scattering that makes Earth's daytime sky opaque to starlight. At 60 astronomical units from the red giant, the stellar illumination is roughly equivalent to a heavily overcast day on Earth, enough to see by, enough to support photosynthesis if the pigments are well adapted, but not the blazing brightness of equatorial noon that characterizes Earth's relationship to the current Sun. Shadows are long and deep red. Colors appear muted, shifted toward the warm end of the spectrum. Beyond the star, the night sky is one of the most visually extraordinary aspects of this environment. At 60 astronomical units from the star, the planet is in the outer solar system, and the perspective on the galaxy and surrounding space differs only modestly from the current Earth perspective. The positions of the background stars shift imperceptibly over the course of a stellar system's evolution. But within the system, the view is transformed. The giant star dominates one side of the sky. The outer planets, whatever remains after the stellar wind has acted on them, orbit at the familiar distances of Jupiter, Saturn, Uranus, Neptune. But the inner solar system is gone. The rocky inner planets, Mercury, Venus, Earth's ghost, Mars, have been either engulfed or sterilized. The asteroid belt has been swept and heated. What remains of the solar system at 60 astronomical units is the outer planetary system, roughly familiar, plus the transformed icy outer bodies that are now warm and active. The seasons on this hypothetical world are driven by its axial tilt, if it has one, and by the eccentricity of its orbit. At large orbital distances, orbital periods are long. By Kepler's third law, the orbital period scales as the distance to the 3/2 power. At 60 astronomical units, the orbital period is 60 to the 3/2 power of AD or X or AE, RA, C or F. A year on this world lasts nearly 5 centuries. The seasonal cycle, if the planet has an axial tilt, plays out over centuries. A single summer hemisphere might receive elevated illumination for 150 years before transitioning through equinox into the long winter of the opposite tilt. These are not seasons in any human experiential sense. They are geological episodes. An observer living through one summer would not survive to see the next. The tidal environment is also dramatically different from Earth's. Earth's tides are driven primarily by the moon, with a significant but smaller contribution from the sun. At 60 astronomical units from a red giant, the stellar tidal force on any planet is negligible. The gravitational gradient across the planet's diameter from a star 60 AU away is far smaller than the lunar tidal gradient on Earth. If the planet has a large moon, the tidal dynamics are similar to Earth. If it does not, if it is a captured body from the outer solar system, or a body that formed without a large moon, the tidal forces are minimal and the planets might rotate slowly or synchronously. Some icy bodies in the outer solar system are tidally locked to their parent planets. A former Kuiper belt body, warmed by a red giant, might be tidally locked to the star if it formed close enough and orbited long enough. What is this? End quote. A tidally locked planet in the red giant's habitable zone would present a fascinating environment, one hemisphere permanently facing the star, bathed in its amber-red glow. The surface temperatures on this hemisphere potentially warm enough for liquid water. The other hemisphere, permanently facing away from the star, cold and dark. Temperatures dropping toward the cosmic microwave background if there is no atmospheric heat transport. The boundary between these hemispheres, the terminator, would be a zone of perpetual twilight, the star hanging always on the horizon, the light filtering across the boundary in a permanent, ethereal dusk. The most habitable region of such a world might actually be this terminator zone, where the temperatures are intermediate, where the star provides sufficient but not overwhelming illumination, where the extremes of both hemispheres are moderated by the circulation of a thick atmosphere, moving heat from the day side to the night side. The atmospheric circulation on a tidally locked world is unlike anything on Earth. On Earth, the day-night temperature difference drives convection that is then shaped by the Coriolis effect of the planet's rotation into the familiar pattern of trade winds, westerlies, and polar jets. On a tidally locked world, the permanent day-night temperature difference drives a single, large convective cell. Hot air rises over the day side, flows at high altitude toward the night side, cools and descends on the night side, returns at low altitude to the day side. The result is a global circulation pattern unlike Earth's, with strong convergent winds toward the substellar point, the point directly under the star, high altitude divergent outflow toward the night side, and cold, subsiding air on the antistellar side. The substellar point would likely be the warmest region, potentially experiencing temperatures significantly above the global mean, while the antistellar point will be the coldest. Cloud cover would be concentrated near the substellar point, where the rising moist air cools and condenses, providing both a visual marker of the hottest region and a reflective feedback that moderates the surface temperature below the clouds. There is a further complexity that makes the red giant environment even more interesting from an atmospheric physics standpoint. The radiation from a red giant is not spectrally identical to the radiation from the Sun. The Sun's spectrum peaks in the visible light range, with substantial UV emission that drives photochemistry in Earth's upper atmosphere, including the formation and maintenance of the ozone layer, which shields the surface from harmful UV radiation. A red giant, with its lower surface temperature, emits far less UV radiation and far more of its energy in the near-infrared. This shift has profound implications for atmospheric chemistry. Without significant UV irradiation, the photochemical reactions that produce ozone from molecular oxygen are much slower. An atmosphere rich in oxygen but orbiting a red giant would develop a much thinner ozone layer than Earth's, or none at all. This would mean that significant UV radiation from any source, from cosmic rays, from stellar flares, from other stars in the galaxy, could reach the surface unimpeded. Conversely, the lower UV flux from the primary star means that the photochemistry that drives some forms of atmospheric escape and molecule dissociation is reduced. Potentially allowing molecules to persist in the atmosphere that would be photodissociated on Earth. Methane, for example, which has a short atmospheric lifetime on Earth because UV radiation breaks it apart, might persist in much higher concentrations in the atmosphere of a planet orbiting a cool red giant. This has interesting implications for biosignatures. A planet orbiting a red giant with abundant methane in its atmosphere might look quite different spectrally from Earth. And detecting signs of life on such a world requires searching for different chemical markers than the ozone-methane combination that makes Earth's atmosphere a biosignature. The implications extend to biology. Life on Earth is remarkably well adapted to sunlight. Chlorophyll absorbs specific wavelengths of visible light that are abundant in the sun's spectrum. Life on a planet orbiting a red giant would face a very different spectral environment. The available photons are predominantly in the near-infrared, not the visible. Photosynthetic organisms, if they evolve, would need to harvest these near-infrared photons efficiently. Some bacteria on Earth already do this. The so-called far-red and near-infrared photosynthetic bacteria, which absorb at wavelengths of 700 to 850 nanometers, beyond the absorption range of chlorophyll. These organisms offer a preview of what red giant adapted photosynthesis might look like, though they would need to extend their absorption even further into the infrared to exploit the peak emission wavelengths of a red giant spectrum. The animal life on such a world, if it evolves, might perceive a very different visual world from humans. Human eyes are adapted to the solar spectrum, which peaks in the green-yellow range. Our peak sensitivity is at roughly 555 nanometers, precisely where the sun is brightest, an elegant example of evolutionary optimization. On a red giant world, the optimal spectral sensitivity for vision would be in the red and near-infrared, where the star's light is most abundant. Organisms with eyes optimized for this spectral range would see a rich, detailed world in wavelengths invisible to us. What appears to a human visitor as a dim reddish gloom would, to a native organism, be a brightly illuminated, spectrally rich environment. Vision in the near-infrared would allow organisms to see heat signatures, the thermal emission of other organisms, of warm rocks, of geothermal features, giving the near-infrared a dual function that visible light on Earth lacks. We have been exploring the case of a planet in the outer solar system warmed by the red giant's elevated luminosity. But there is a third version of this thought experiment that is also worth exploring. What happens to the existing outer planets of the solar system when the sun becomes a red giant? Not a hypothetical external Earth at 60 AU, but the actual planets at their actual current distances: Jupiter, Saturn, Uranus, Neptune, under the red giant sun. Jupiter, at 5.2 astronomical units, would receive 2,700 times more solar radiation than it does today. The equilibrium temperature at Jupiter's orbital distance scales by the same fourth root of luminosity factor we applied to Earth, giving an equilibrium temperature increase by a factor of 7.2, but starting from Jupiter's current effective temperature of about 110 Kelvin, not Earth's 255 Kelvin. Jupiter's new equilibrium temperature would be approximately 790 Kelvin, about 520 degrees Celsius. The upper cloud layers of Jupiter, which currently consist of ammonia ice crystals at temperatures around 165 Kelvin, would be completely vaporized. The deeper cloud layers, ammonium hydrosulfide clouds, water clouds, would follow. Jupiter's distinctive banded structure, driven by the differential heating of ammonia and water clouds at different altitudes, would be transformed entirely. The upper atmosphere would become dominated by water vapor and other thermochemical products at these extreme temperatures. What happens deep in Jupiter's interior under red giant heating is less certain but fascinating to model. Jupiter already emits more heat from its interior than it receives from the current Sun, a remnant of the gravitational energy released when the planet formed and its mass contracted. Under the red giant, the external heat input at the upper atmosphere would dwarf this internal heat flux, driving a thermal gradient that runs in the opposite direction from today's, not from hot interior to cold space, but from hot exterior radiation down into the cooler interior. The dynamics of Jupiter's atmosphere under these conditions, with intense external heating from above, continued internal heat from below, and no solid surface to anchor weather patterns, would be unlike anything in the current solar system. But the most significant changes at Jupiter are not to the planet itself, but to its moons. The Galilean moons, Io, Europa, Ganymede, and Callisto, are currently distributed between 782,700 kilometers from Jupiter, and they represent 4 entirely different types of icy or rocky body. Io, the innermost, is already volcanic, the most volcanically active body in the solar system, kept molten by the intense tidal heating from Jupiter. Europa, with its smooth ice surface and subsurface ocean, is the solar system's most celebrated candidate for extraterrestrial life. Ganymede, the largest moon in the solar system, at 5,268 kilometers in diameter, has its own magnetic field, the only moon known to possess one. Callisto is a heavily cratered, differentiated, but geologically quiet ice rock body. Under the red giant sun, all 4 would be dramatically transformed. The equilibrium temperature at Jupiter's orbital distance from the red giant, as we calculated, is about 790 Kelvin. But this is the temperature for a body in direct orbit around the star. The Galilean moons, orbiting Jupiter, receive both the direct stellar radiation and the thermal emission from Jupiter itself, which would be radiating copiously at its elevated temperature. The net radiation environment on the Galilean moon surfaces would be even more intense than at Jupiter's orbital distance alone. At 790 Kelvin, water ice sublimates rapidly. The sublimation rate increases exponentially with temperature, and at this temperature, the ice surface would sublime in a matter of years or decades, rather than the geological timescales over which ice remains stable in the current solar system. Europa's ice shell, currently estimated at 10 to 30 kilometers thick, would completely sublime into space over perhaps a few thousand to tens of thousands of years. The ocean beneath, estimated to contain twice the volume of all Earth's oceans combined, would be directly exposed to space and to the intense radiation. the exposed ocean surface would warm, evaporate, and eventually boil. Whether the ocean could remain liquid long enough for any significant chemical or biological processes to occur in the fully exposed state depends on the rate of evaporation versus the rate of stellar energy input, a balance that favours rapid evaporation. However, there is a period before the complete loss of the ice shell, during which Europa's conditions might be extraordinary. As the ice shell thins from above, the thermal input increases, and the subsurface ocean, already warmed by the current tidal heating from Jupiter, warms further. The ocean chemistry changes as hydrothermal vents in the seafloor continue to inject minerals and energy into the water column. The thermal gradients that currently drive chemical energy gradients in Europa's ocean, the contrast between the cold water near the ice-covered top and the warmer water near the hydrothermal vents, would be amplified rather than diminished in the early warming phase. If life currently exists in Europa's ocean, this period of intensified energy input might actually be beneficial. More chemical energy available, more mixing, potentially richer gradients for chemosynthetic metabolism. The transition from ice-covered ocean to exposed ocean marks the end of this potentially productive phase. Once the ice shell is gone, the ocean is exposed to the radiation and stellar wind of the red giant directly. The surface water evaporates. The water vapor is blown away by the stellar wind. Over millions of years, the ocean slowly evaporates into space, driven off as steam by the relentless heating. What remains after the ocean is gone is Europa's rocky core, a silicate and iron body roughly 1,000 kilometers in radius, bare and dry, orbiting Jupiter in a vastly transformed environment. Ganymede's fate is similar, but modified by its own magnetic field. The magnetic field, generated by convection in Ganymede's iron core, provides some protection against the stellar wind, analogous to Earth's magnetosphere, though much weaker. Whether this protection is sufficient to meaningfully slow atmospheric and surface ice loss under red giant conditions is uncertain. Probably not. The stellar wind enhancement is so dramatic that even Earth's magnetosphere struggles, and Ganymede's weaker field offers proportionally less protection. But the presence of a magnetic field makes Ganymede's transformation more complex and interesting than a simple ice-to-rock conversion. The magnetic field interacts with the thermal and particle environment in ways that influence the rate of atmospheric sputtering and the chemistry of whatever transient atmosphere develops from the subliming ice. Saturn's system would be transformed even more spectacularly. Saturn, at 9.5 astronomical units from the Sun, currently receives about 1% of Earth's current solar flux. Under a red giant with 2,700 times the luminosity, Saturn receives 27 times Earth's current solar flux, equivalent to what a planet at about 0.2 astronomical units from the current Sun receives, closer than Mercury. Saturn's atmosphere, currently characterized by its pale bands of ammonia clouds and complex hydrocarbon chemistry in the upper troposphere, would be fundamentally altered. The distinctive amber-colored bands and the subtle chemistry driven by photolysis of ammonia and phosphine will be replaced by a much hotter, chemically different atmosphere, dominated by water vapor, carbon dioxide from the interior, and thermochemical products of the intense heating. But it is Saturn's ring system that undergoes perhaps the most visually dramatic transformation. The rings of Saturn, the most extensive and visually striking ring system in the solar system, extending from about 7,000 to 80,000 kilometers above Saturn's equator, consists primarily of water ice particles ranging from millimeter to meter sizes, with a small admixture of rocky material. At Saturn's current distance, these ice particles are stable, cold enough that sublimation is negligible, and the particle collisions and orbital dynamics that maintain the ring structure are well understood. Under the red giant sun, the ice particles warm to temperatures far above the sublimation point for water ice and sublime rapidly. The rings of Saturn would disappear, evaporated into a thin haze of water vapor that is then blown away by the stellar wind. Saturn without its rings, a pale, featureless globe orbiting in the transformed outer solar system, its most iconic feature gone. Titan's fate is among the most complex and scientifically interesting in the entire scenario. Titan is unique in the solar system, the only moon with a thick atmosphere comparable to Earth's, with a surface pressure of 1.45 bar and an atmospheric composition primarily of nitrogen, 98.4%, and methane, 1.6%, with trace quantities of dozens of complex organic molecules produced by the photochemical reactions of nitrogen and methane in the upper atmosphere. The orange haze that gives Titan its characteristic colour consists of tholins, complex organic polymers produced by these reactions, coating Titan's surface in a global layer of dark, complex organic material that is, in terms of prebiotic chemistry, extraordinarily rich. As the red giant heats Titan, the methane sees on its surface, currently at 94 Kelvin, 3 Cs of liquid methane, covering perhaps 1.5% of the surface in the polar regions, begin to evaporate. The methane evaporates first, since its boiling point is only 112 Kelvin at standard pressure. As the methane seas evaporate, the atmospheric methane concentration increases, and the photochemical reactions in the upper atmosphere intensify. The tholins and other organic compounds on the surface begin to sublime and decompose. Water ice, which makes up a significant fraction of Titan's interior and appears as surface exposures in some regions, begins to warm. As temperatures climb above 273 Kelvin, the melting point of water ice, the water ice in Titan's crust begins to melt. This is the extraordinary moment. Titan has spent 4.6 billion years accumulating complex organic chemistry at its surface, driven by photochemistry and meteorology that are unlike anything elsewhere in the solar system. The tholins and other organics on its surface represent the most extensive natural laboratory of prebiotic chemistry in the solar system. When the water ice in Titan's crust begins to melt, that water comes into contact with the organic chemistry on and near the surface. This is the contact between water and organics that many origin of life researchers consider a key trigger for prebiotic chemistry, the same contact that happened on Earth in its early oceans when water dissolved the organic compounds brought to Earth's surface by meteorites and produced in its early atmosphere. On Titan, this contact happens for the first time at the moment of red giant warming, after 4.6 billion years of separate preparation, 4.6 billion years of chemistry building up organic compounds, and then, suddenly, water. The organic chemistry on Titan is in many ways more complex than what was available to early Earth. The tholins contain amino acid precursors, nucleobase-like compounds, and complex carbon-nitrogen-oxygen heterocycles that are among the most sophisticated natural organic synthesis products known. If the contact between this chemistry and liquid water, under the energy input of the red giant, is sufficient to trigger the emergence of life, then Titan's red giant phase would be the birth of a biosphere, the first and only biosphere this moon ever knows, arising in the warmth of a dying star with a legacy of 4.6 billion years of organic chemistry as its founding endowment. This possibility is taken seriously by astrobiology researchers. It is not confirmed, and it requires assumptions about the speed of life's emergence that are not yet validated. But it illustrates the deeply counterintuitive nature of the red giant transition. The same event that ends the biosphere of Earth simultaneously creates the chemical conditions for the possible emergence of biospheres on the moons of Saturn and Jupiter. The dying star is simultaneously a catastrophe and a beginning, depending on your distance from it. This is the fundamental asymmetry at the heart of the question. The planets that benefit from the red giant's warmth are the ones that are currently too cold to be habitable. The planets that are currently habitable are destroyed by the same fire that warms the outer system. There is no universe in which both Earth and Titan are simultaneously in the habitable zone of the Sun. The physics of stellar luminosity and the distances of the solar system's planets are such that either the outer planets are habitable, and the lost continent did so. Inner planets are habitable, or inner planets are habitable, or the outer are frozen. The Sun cannot be both mild enough for Earth and intense enough for Titan. It is one or the other, and the transition from one state to the other is a catastrophe for everything that had been living in the previously habitable zone. This asymmetry has a deep implication for the distribution of life in the universe and for what we might expect to find when we search for biosignatures on exoplanets. There are likely many planets in the galaxy that are, right now, in the warm zone of a red giant star, former icy worlds, recently thawed, experiencing their first era of habitability. If life can arise on timescales of hundreds of millions of years, some of these worlds might already harbour life. Their biosignatures, the chemical traces of living systems in their atmospheres, would be detectable, in principle, by a sufficiently sensitive space telescope. But they would look different from Earth's biosignatures. Not the oxygen-ozone-water combination that Earth presents. Something adapted to the different chemistry, different spectral environment, different geological history of a world that spent its first 5 billion years frozen before experiencing a sudden geological spring. The red giant sun is in this sense not merely a catastrophe for the inner solar system, it is a reshuffling, a redistribution of the zone of potential habitability from the inner planets, where it has sat for 4.6 billion years, to the outer planets and moons, where it arrives suddenly and briefly, a flash of warmth in the long cold dark of the outer solar system, offering new possibilities to worlds that have waited patiently in the freeze for their moment. The catastrophic and the opportunity are the same event, experienced from different distances. This reshuffling is not merely theoretical. Astronomers are now beginning to search for it directly. The Kepler Space Telescope, which operated from 2009 to 2018 and detected thousands of exoplanets by watching for the slight dimming of a star as a planet passes in front of it, found planetary systems around stars at all stages of evolution, including around evolved, post-main sequence stars. Several planets have been detected around giant stars. The radial velocity method, which detects the slight wobble of a star caused by the gravitational tug of an orbiting planet, has been particularly productive for planets around giant stars. Because the large size and slow rotation of giant stars produce spectral lines that are easier to measure with high precision than the narrower lines of faster rotating main sequence stars. Surveys specifically targeting giant stars have found dozens of giant planets, Jupiter mass and larger, in orbits at several astronomical units from their host stars. What these surveys have so far been unable to detect is small, rocky planets in the outer reaches of evolved stellar systems, the former icy worlds that might be the sites of transient habitability. Small planets produce smaller Doppler wobbles and shallower transit signals, making them harder to detect around any star, and giant stars are even more challenging due to their inherent brightness variability, which can mask small planetary transit signals. The James Webb Space Telescope, with its extraordinary sensitivity in the infrared, the spectral range most relevant for the cooler temperatures of both red giants and the outer solar system bodies they warm, offers the possibility of characterizing the atmospheres of planets around evolved stars for the first time. If a rocky planet orbiting in the habitable zone of a red giant has a biologically modified atmosphere, one containing disequilibrium combinations of molecules like oxygen and methane that can only persist if continuously replenished by living water. Organisms, JWST, might detect these biosignatures in the transmission spectrum of the planet's atmosphere as it transits the star. This is not speculative in the sense of requiring exotic physics. The same techniques that JWST is currently applying to characterize the atmospheres of rocky planets around nearby red dwarf stars, TRAPPIST-1e, LHS-1140b, and others, are applicable to planets around red giants, with the caveat that the distances to red giant systems are typically much greater, requiring much brighter stars or much closer systems to produce detectable signals. But within the solar neighborhood, within perhaps 100 to 200 light-years, there are a number of giant stars, some of which have confirmed planetary companions, that are in principle accessible to this kind of atmospheric characterization with future extremely large telescopes. The broader implication is profound. If red giant stellar evolution routinely creates transient habitable conditions in the outer reaches of formerly inner system stellar systems, and if life can arise on these former icy worlds during the red giant phase, then there may be a population of inhabited or recently inhabited worlds associated with giant stars throughout the galaxy. These worlds would not be in the traditional habitable zone of a main sequence star. They would not look like Earth. Their biosignatures would be different, adapted to the spectral environment of a red giant, to the chemical composition of an icy world recently thawed, to the different gravitational and tidal environment of an outer solar system body. But they would be there, if life is as robust as its origin on Earth suggests. Consider how this changes the statistical calculation for life's prevalence in the galaxy. Currently, Most estimates of the number of habitable worlds focus on rocky planets in the habitable zones of main sequence stars. This is a reasonable starting point, but it may significantly undercount the total number of habitable environments if red giant transient habitability is common. A solar mass star spends roughly 10 billion years on the main sequence, during which its habitable zone may harbour 1 or 2 rocky planets for a fraction of that time. But during the red giant phase, which lasts perhaps 1 to 2 billion years, a much larger number of bodies, the icy moons of gas giants, large Kuiper belt analogues, outer rocky planets with ice mantles, are potentially warmed into habitability simultaneously. If even a small fraction of these bodies develop life during the billion-year red giant window, the contribution to galactic life prevalence could be significant. There is even a scenario, speculative but not absurd, in which the origin of life itself is more likely during the red giant phase than during the main sequence phase for some planetary systems. The argument goes as follows. Life's emergence requires not just the right temperature and liquid water, but a rich supply of complex organic molecules in contact with mineral surfaces and energy gradients. In the outer solar system, complex organic chemistry has been accumulating for billions of years. Driven by the energetic chemistry of the solar nebula, during planet formation, and by cosmic ray and UV-driven chemistry in the interstellar medium that contributed to the icy planetesimals from which the outer solar system bodies formed. These outer bodies are, in organic chemical terms, richer than the inner rocky planets, which were stripped of their most volatile organic compounds by the heat of their formation close to the young sun. When the red giant warming brings liquid water to these organically rich outer bodies, it may be providing a better substrate for life's emergence than anything available in the inner solar system. The astrobiologist Siegfried Frank and colleagues have specifically modelled the potential habitability of former icy worlds in the outer solar system during the red giant phase, finding that for solar mass stars, the transient habitability window of certain outer solar system regions could last 1 to 2 billion years, comparable to the time it took life to emerge on Earth. The modelling suggests that the red giant phase of solar-type stars may be a cosmically significant epoch for life's emergence, not merely an endpoint for the life already present in the system. This is a reversal of the usual narrative. In the usual narrative, stars create life on their inner planets during the main sequence and then destroy it during the red giant. In the revised narrative, stars may do their most important work for life at the end, not the beginning, of their main sequence phase. And when the red giant phase ends, when the sun has expelled its outer layers and the planetary nebula has faded, and what remains is the white dwarf at the centre, a dim, Earth-sized object emitting only the stored heat of its compressed carbon-oxygen core with no ongoing nuclear reactions, the outer solar system freezes again. The former icy worlds, briefly thawed, refreeze. The liquid oceans on the exposed Galilean moons solidify. The temporary atmospheres condense and settle as frost on the surface. The era of warmth is over. The outer solar system returns to its cold, dark equilibrium, carrying within the geology of those briefly warmed worlds the chemical record of what happened during the red giant phase, and perhaps, if life arose, the biological record as well, preserved in the permafrost of a frozen biosphere, waiting for the light that will not come again. The white dwarf sun, cooling slowly over trillions of years, provides essentially no heat to the outer solar system. The habitable zone of a white dwarf, a body with the mass of the sun compressed into the volume of the Earth, its luminosity initially comparable to the sun, but declining steadily, is extraordinarily small and shifts inward and narrows as the white dwarf cools. A newly formed white dwarf might maintain a habitable zone, a few percent of an AU, for the first few billion years of its existence, slowly retreating towards zero. Any planet orbiting in this zone must have either migrated inward during the red giant phase or arrived through dynamical interactions following the star's dramatic evolution. Several white dwarfs have been found to show evidence of planetary material. The spectra of their atmospheres show elements heavier than hydrogen and helium, which sink rapidly under the white dwarf's intense gravity unless continuously replenished, suggesting ongoing accretion of rocky or icy planetary debris. A few have been found with confirmed planetary companions. The white dwarf planetary system is a transformed, diminished version of what the original system was, a quiet endgame for the stellar and planetary evolution that began billions of years earlier in a molecular cloud, paid out over the incomprehensible span of stellar lifetimes, ending in the slow, perpetual calling of a stellar remnant no larger than the Earth. This is ultimately what the question, what if Earth was orbiting a red giant star, is really about. Not just the fate of one planet, but the redistribution of the conditions for habitability across an entire planetary system, driven by the inexorable internal physics of stellar evolution. The star is not doing anything perverse or unusual. It is doing exactly what physics requires of a star of its mass, consuming its fuel, adjusting its structure to the changing energy sources available, expanding and contracting, and expanding again in the sequence that stellar theory predicts with extraordinary precision. The planets are passive recipients of these changes. They have no agency. They cannot adjust their orbits to stay in the habitable zone as the star evolves. They are carried along by gravity, fixed in their orbital paths, experiencing in succession the conditions that each phase of their star's life produces at their particular distance. What makes this question so philosophically rich is that it confronts us with the contingency of our own existence. We live on Earth at one astronomical unit from the Sun, in the main sequence phase of the Sun's life, during the period when this particular distance is inside the habitable zone. Every one of those conditions is contingent. Change any one of them, move the Earth closer to the Sun, age the Sun by 5 billion years, change the Sun's mass slightly, and the conditions for complex life as we know it either do not exist, or have not yet arrived, or have already ended. The habitable zone is not a permanent feature of a stellar system. It is a moving window, defined at any moment by the current luminosity of the star, sweeping outward as the star ages and brightens, turning former frozen tundra into warm ocean and former warm ocean into lava, a travelling zone of potential that passes through any given orbital distance only once and for a finite time. Earth happens to be in the habitable zone right now. It has been in the habitable zone approximately for the past 4 billion years, during which life has evolved from simple chemistry to the extraordinary complexity of the current biosphere. This is not guaranteed, it is fortunate. It is the result of a star with the right mass, orbiting in the right configuration, with the right amount of geological and atmospheric feedback to maintain habitable conditions despite the Sun's gradually increasing luminosity over those 4 billion years. Without the carbonate-silicate weathering cycle, the geological thermostat that sequesters carbon dioxide into rocks when temperatures rise and releases it when temperatures fall, Earth would have become uninhabitable much sooner, as the young Sun brightened Without the right inventory of volatile elements in Earth's initial formation, the oceans might never have formed. Without plate tectonics to recycle the carbonate rocks and replenish the atmospheric carbon dioxide, the carbon cycle would have stalled long ago. The habitability of Earth over 4 billion years is not just the product of being at the right distance from the Sun. It is the product of a complex, interconnected system of geological, chemical, and atmospheric feedbacks that have maintained conditions within the narrow range compatible with liquid water and active chemistry. All of that system fails catastrophically in the red giant scenario. Not because the system is fragile in isolation, it has proven remarkably robust over 4 billion years of the Sun's gradual brightening, but because the red giant's luminosity increase is not gradual in geological terms. A factor of 2,700 increase in luminosity over a period of perhaps 1 billion years, rapid in geological terms, compared to the 4 billion year gradual increase of the current solar main sequence, overwhelms every feedback mechanism. The carbonate silicate weathering cycle, which can compensate for gradual luminosity increases by drawing down atmospheric carbon dioxide, cannot draw down CO2 fast enough when the luminosity is increasing by thousands of percent. The rate of weathering depends on temperature and precipitation. If the temperature is rising faster than weathering can compensate, the feedback loop fails. In the red giant scenario, the temperature rise is so rapid and so extreme that weathering is irrelevant. Long before the carbonate silicate cycle could stabilize the climate, the oceans have evaporated and the surface has become molten. This means that the habitability of a planet orbiting a red giant is not simply a matter of orbital distance, it is also a matter of timing. A planet that happens to orbit at 50 to 70 astronomical units when the star enters the red giant phase finds itself in the habitable zone for the first time. But whether it can maintain habitable conditions for long enough for life to emerge and evolve depends on the rate of change of conditions, whether the temperature rises gradually enough that geological and atmospheric feedback mechanisms can respond, or whether the warming is so rapid that no stabilizing mechanism can keep up. The outer icy bodies that are warmed by the red giant have the advantage of starting very cold, far below habitable temperatures, so that the warming must proceed through a large temperature range before reaching the habitable window. This gives the geological and chemical systems time to respond. As the temperature climbs from 50 Kelvin toward 273 Kelvin, the interior warms, base begins to melt, gases are released, an atmosphere develops, greenhouse warming kicks in. All of these processes happen in sequence, each building on the last, over perhaps hundreds of thousands to millions of years. This is not fast by human standards, but it is gradual enough that feedback mechanisms can operate. It is a fundamentally different situation from Earth at 1 AU, where the full 2,700-fold luminosity increase arrives immediately and overwhelmingly. The geology of a warming former icy world also differs from Earth's in ways that might actually favour rapid ability establishment. As the ice mantle of a large icy body melts, the liquid water percolates downward through the rock, reacting with fresh silicate surfaces that have never been in contact with liquid water before. The chemical reactions between liquid water and fresh silicate rock, hydrothermal alteration, serpentinization, oxidation, release hydrogen gas, dissolve minerals, and create geochemical gradients. These reactions are among the most productive sources of chemical energy for life on Earth today. Deep-sea hydrothermal vents, where hot, mineral-rich water meets cold ocean, host rich ecosystems entirely independent of sunlight. On a warming icy world, as the first liquid water percolates through the rock, similar geochemical reactions occur everywhere the water reaches fresh rock, creating a global hydrothermal system rather than isolated vent fields. The entire planet might be a hydrothermal vent, in a sense. During its initial thaw, a chemical, energy-rich environment, well before photosynthesis could develop, if photosynthesis is what life requires. Earth, in the red giant scenario, does not survive. Not in any form we would recognize. Not as a planet with oceans and atmosphere and geological activity and the possibility of life. It becomes, first, a hell of boiling seas and scorched sky. Then, a furnace of molten rock and rock vapor atmosphere. Then, as the star eventually cools and the thermal equilibrium drops, a bare, airless rock, its continents gone, its ocean basins filled with resolidified basalt, its history erased from the surface layer. The interior preserves its record, the deep geological structures of billions of years of plate tectonics, the iron core, the mantle's chemical heterogeneity built up over the age of the solar system. But the surface is new, blank, featureless. A clean slate drawn by fire. And yet, within this catastrophe, there is something that deserves to be recognized for what it is. The profound indifference of physics to our preferences. Combined with the profound generosity of physics in making something possible at every scale and every distance, if the conditions are right. The red giant sun that destroys Earth simultaneously thaws Europa, unfreezes the Kuiper Belt, warms the methane seas of Titan, and potentially seeds half a dozen formerly frozen worlds with the conditions for chemistry to try something new. The same fire that ends one chapter writes the opening lines of another. Not for us, not for anything we would recognize as ours, but for the chemistry that continues, the water that flows again, the molecules that arrange and rearrange in the warmth of a dying star, trying, as chemistry always tries when the conditions permit, to become something more.